Every single particle you know might have a hidden twin. This is the startling proposal of supersymmetry, a theory suggesting a shadow universe of partner particles for every one we have already discovered. By the end of this, you will see how this single idea could completely rewrite the laws of physics. It promises to explain the invisible dark matter holding galaxies together and open doors to technologies we can barely dream of. Why has this cosmic mirror world remained utterly invisible to us, and what would it take to finally catch a glimpse? What do you think is the most profound secret the universe is still keeping from us? Think of our universe as a stage, and the standard model provides the entire cast of characters. The quarks are the building blocks coming together to form protons and neutrons inside every atom. Then you have the leptons, a family that includes the familiar electron, and you cannot have a play without action, which is where the force carriers come in. The photon brings us light, the gluon holds atomic nuclei together, and other particles mediate forces like the weak nuclear interaction. This cast has performed flawlessly, predicting the outcomes of countless experiments. Yet for all its success, the script is missing some crucial pages. The performance is happening on a stage we cannot fully see, with major roles played by actors who never show their faces. This model says nothing about the dark matter that gravity tells us must be there, binding galaxies. It cannot explain why gravity itself is so unimaginably weaker than the other forces. We have a brilliant theory that describes the visible universe, but it is a theory that is profoundly, undeniably incomplete. That gap between what we know and what we must explain is the very space where new ideas are born. This gap in our cosmic play is exactly where supersymmetry makes its entrance. It proposes a breathtakingly elegant solution, a hidden symmetry woven into the fabric of reality itself. The core idea is both simple and profound. For every known type of particle, there exists a secret partner. Think of it like this: our universe has two great families of particles. The fermions are the solid stuff, the building blocks of matter like quarks and electrons. Then you have the bosons, the messengers that carry forces like photons and gluons. Supersymmetry suggests that for every single fermion, there is a boson partner waiting in the wings, and for every boson, there is a corresponding fermion twin. It is a perfect one-to-one mirroring. Imagine the entire cast of our standard model play, but now every single actor has a dedicated stunt double. The lead actor, an electron, has a super partner called the selectron. The powerful gluon has a partner called the gluino. Every particle we know would be paired with a super particle we have yet to meet. This is not just about adding more characters to the list. This theoretical doubling does something miraculous. It creates a bridge between the two great families of the universe, matter and force. It suggests that at a fundamental level, they are not so different after all. They are two sides of the same cosmic coin. This is the grand promise of supersymmetry, a potential unified theory of everything. It is a prediction that has not yet been confirmed by any experiment, a shadow cast by our mathematics. But if it is real, it would mean we have been living next to an entire hidden universe this whole time, a realm of superpartners just out of sight. These hidden twins even have their own collective name, sparticles. It is a playful term for a profound idea, making this shadow cast of characters feel just a little more real, and there is a simple, almost charming logic to how each one is named. For the super partners of the familiar matter particles, the fermions, we just add an S at the beginning. The electron gets its selectron. The different types of quarks, like the up quark and down quark, get their corresponding squarks. It is as if each piece of tangible stuff in our world has a secret, superpowered counterpart. But what about the partners for the force carriers, the bosons? Their naming convention is just as straightforward, ending with the suffix ino. The photon, the particle of light, would be paired with the photino. The gluon, which so powerfully binds quarks together, has a partner called the gluino. So you have the s particles for matter and the ino particles for force. This elegant naming system does more than just create a catalogue of hypothetical entities. It gives us a language to discuss this hidden world, transforming an abstract mathematical symmetry into a tangible, almost familiar family of potential discoveries. The selectron is not just a name, it is the specific superpartner to the electron. The photino is the specific missing half of the photon. This makes the entire concept feel less like a vague theory and more like a detailed map to a treasure we have not yet found. So let us meet the selectron, the first of these hidden twins to step into the light. If the electron is the fundamental unit of electricity, the bedrock of our digital world, then its superpartner is something entirely different. The selectron is a boson, a force-like particle born from the same mathematical heart as the electron itself. This single change in its fundamental nature has staggering consequences. While the familiar electron possesses a property called spin, a tiny intrinsic angular momentum, the selectron would have zero spin. It would be still and stable in a way that matter particles simply are not. This stability is the key to its potential. Imagine a new form of matter built not from restless, spinning electrons, but from these placid selectrons. They would not repel each other as electrons do. They could cluster together, creating incredibly dense and stable structures. This could lead to batteries with energy densities we can scarcely conceive, powering devices for years or enabling city-sized grids with unprecedented efficiency. The discovery of the selectron would not just add a new particle to a chart. It would hand us the key to a new kingdom of materials science, rewriting the rules of electronics from the ground up and giving us mastery over energy itself. What kind of world could we build if we learned to command the electron's silent twin? But the selectron is just the beginning of this hidden family. The quarks that form the very core of our atoms also have their own superpartners, known collectively as the squarks. There are 6 types mirroring the up, down, charm, strange, top, and bottom quarks of our world. These squarks are not just exotic additions to a particle list. They hold the potential to solve one of the most puzzling problems in all of modern physics, the hierarchy problem. This is the mystery of why the Higgs boson, the particle that gives all others mass, is so surprisingly light. Our current math suggests it should be astronomically heavier, pulled to an immense scale by its interactions with other particles. This is where the squarks come in. Their theoretical existence provides a perfect, natural cancellation. The squark's own interactions with the Higgs would precisely counterbalance the effects of the regular quarks, effortlessly stabilizing its mass to the tiny value we observe. It is as if the universe employs a perfect set of counterweights, and squarks are the missing piece that makes the delicate balance possible. Finding them would not just confirm a symmetry. It would show us why the universe is even able to have stable atoms, and by extension us. The hunt for these particles is a central goal of the world's most powerful atom smashers. When protons collide at nearly the speed of light, the immense energy could, for a fleeting instant, be converted into the mass of a squark. They would not last long, decaying almost instantly into other particles, leaving behind a unique signature in the detectors. And this process of creation and decay might hold another profound clue: the slight ways in which squarks and their anti-particle counterparts could behave differently might explain one of the universe's oldest mysteries. Why is the cosmos filled with matter with almost no antimatter to be found? The squarks could be the key that unlocked the primordial imbalance, the reason anything exists at all. While squarks offer answers to the stability of matter, another set of twins could answer the question of what holds the cosmos together. Meet the sneutrinos, the superpartners to the most ghostly particles we know, neutrinos. Neutrinos are the phantoms of the subatomic world, streaming from the sun and distant stars in uncountable trillions. yet they barely interact with anything passing through our planet as if it were empty space. Their superpartners, the sneutrinos, would be fundamentally different. A neutrino is a fermion, a piece of matter, but a sneutrino would be a boson, a particle of force. This shift in identity gives it a property its twin lacks, the potential for stability. While regular neutrinos zip through the universe at nearly the speed of light, a sneutrino could be slow, heavy, and incredibly long-lived. It would not be pushed and pulled by electromagnetic forces, and it would barely feel the strong nuclear force. This makes it a perfect, and I mean a perfect, candidate for the invisible substance we call dark matter. Imagine a universe filled with a vast, unseen ocean of these sneutrinos. Their collective gravity would be the cosmic glue that binds galaxies, preventing stars from flying apart as they spin. They would form the hidden scaffolding upon which the entire visible universe is built. We have been searching for the identity of dark matter for decades, and the answer might not be a single, exotic particle, but the silent, bosonic twin of a ghost we already know. The discovery of the sneutrino would do more than complete a particle family. It would illuminate the dark architecture of the cosmos, revealing the hidden framework that has shaped everything we see. Beyond the electron's silent twin lie even more elusive partners. The muon and the tau are like the electron's heavier, more unstable siblings, and they too are predicted to have their own superpartners, the smuon and the stau. These are not merely copies of the selectron. Their defining feature is their immense mass, a property inherited from their standard model twins. This sheer weight makes them prime targets for our most powerful experiments. Inside the colossal detectors of the Large Hadron Collider, physicists are not looking for the particles themselves, as they would decay in a fraction of a nanosecond. Instead, they hunt for the energy that goes missing after a collision, the telltale signature of a massive, invisible particle being created and then instantly vanishing. A smuon or a stau, by virtue of its tremendous mass, would leave a colossal energy deficit, a gap in the accounting that screams new physics. Finding one would be like discovering a footprint from a creature we have only ever theorized. The very existence of these heavy sparticles would reveal a hidden structure within the particle world, a clear hierarchy. It would tell us that the symmetry between particles and their superpartners is not a simple one-size-fits-all rule, but a complex, layered principle where mass plays a fundamental role. Why would the universe create such a heavy shadow family? Their discovery could be the first step toward understanding the very architecture of this hidden cosmic mirror. Yet the story of these superpartners grows even more intricate. Beyond the selectrons and sneutrinos, we find the charginos and neutralinos, sparticles born from a cosmic mixing of forces. They are not the pure partners of a single particle, but rather complex quantum blends. Imagine taking the superpartners of the Higgs boson and the particles that carry the electroweak force, the very force that governs radioactive decay and is tied to electromagnetism. Now picture these sparticles merging, their identities blurring to form entirely new hybrid states. The charginos carry an electric charge, while the neutralinos are, as their name suggests, completely neutral. And it is here, in this family of mixed particles, that we might find the single most important sparticle of all. The lightest neutralino is a perfect candidate for the substance of dark matter. It would be stable, massive, and interact with ordinary matter only through gravity and the weak nuclear force, making it nearly impossible to detect directly. This is the profound promise of supersymmetry made tangible. It is not just an abstract mathematical beauty, but a theory that directly points to the invisible matter sculpting the cosmos. Finding a neutralino would not merely complete a particle chart, it would illuminate the dark skeleton of the universe, revealing the hidden form of the very stuff that holds our galaxy together. What would it mean to finally see the face of the cosmic architect? The strong nuclear force holds the very heart of matter together, and its carrier is the gluon. Now we meet its superpartner, the gluino. This is a profound shift in identity. The gluon is a boson, a force carrier, but the gluino is a fermion, a particle of matter. This means the silent twin of the glue that binds the universe is itself a solid piece of substance. The gluino possesses one of the most bizarre properties in all of physics. It is what we call a Majorana particle, a particle that is its own antiparticle. Think of an electron and its antimatter counterpart, the positron. They are opposites, and if they meet, they annihilate in a flash of energy. But a Majorana particle like the gluino has no such distinction. It is its own opposite. It is matter and antimatter folded into a single, enigmatic entity. This self-annihilating nature is not just a theoretical curiosity. It could explain why our universe is made of matter and not just light. In the earliest moments of the cosmos, gluinos could have decayed in a way that subtly favored the creation of matter over antimatter, tipping the cosmic scales to allow everything we see to exist. When a gluino is created in a high-energy collision, its journey is anything but simple. It does not travel far. Instead, it immediately grabs hold of the quarks and gluons flooding the detector, forming a bizarre composite object known as an R-hadron. Imagine a standard proton or neutron, but with a gluino trapped at its core, a heavy, exotic heart within a familiar shell. This R-hadron would be electrically charged, allowing it to leave a clear, ionizing track as it zips through the detector. But then, something truly strange would happen. Because the gluino is so massive, the R-hadron would be incredibly heavy, and it could actually change its charge as it moves. It might start its journey with a positive charge, then interact and flip to neutral, and then flip again to negative. In the data, this would look like a particle track that suddenly vanishes, only to reappear moments later from a completely different point. It would be a ghost in the machine, a signal so dramatic and unexpected that it could not be mistaken for anything else. The hunt for the gluino is a hunt for this very signature, a search for a particle that defies our conventional understanding of matter and identity. The photino presents a fascinating puzzle. As the superpartner to the photon, the very particle of light, you might expect it to be a leading candidate for the dark matter that fills our universe. Yet in the complex dance of supersymmetry, it rarely takes that central role. The photon is a massless, chargeless boson, a perfect messenger of the electromagnetic force. Its twin, the photino, is a fermion, a piece of matter, and theory suggests it should also be massless. A massless particle, however, could not be the source of dark matter's powerful gravitational pull. It would zip through the cosmos at the speed of light, unable to clump together and form the gravitational wells that hold galaxies in place. So the photino must gain mass, and it does so through a remarkable process. It does not stand alone. In the hidden sector of superparticles, the photino mixes quantum states with its cousins, the xeno and the neutral Higgsino. This blending of identities creates the composite particles we call neutralinos. The photino's essence is still in there, but it is now part of a heavier, more stable particle that possesses all the right qualities to be the dark matter we are searching for. This intricate mixing is a crucial lesson. The hidden universe is not a simple mirror. It is a rich tapestry where identities merge and transform, creating the stable, massive entities that can truly shape the cosmos. The search for dark matter, therefore, is not a hunt for a single, pure particle like the photino, but for the unique and stable mixtures that result from this cosmic alchemy. Moving deeper into the heart of the atom, we encounter the massive W and Z bosons. These are not the peaceful carriers of light like the photon, but the powerful mediators of the weak nuclear force, responsible for processes like radioactive decay. Their sheer mass is a mystery in itself, a puzzle tied to the Higgs mechanism, and according to supersymmetry, they too have their hidden twins, the wino and the xeno. These sparticles are not just minor additions, they are central players in one of the most profound unifications in physics, the electroweak sector. This is the theory that elegantly merges the electromagnetic force with the weak nuclear force, showing they were one and the same in the early hot universe. The detection of a wino or a xeno would be more than just another discovery. It would be a smoking gun for supersymmetry. Their unique properties and the precise ways they would interact would provide undeniable proof that this hidden symmetry is real. But their importance goes even further. The way these sparticles mix with others, like the Higgsino, directly influences how the Higgs field gives mass to all other particles. Finding the wino and xeno would not just confirm a theory, it would hand us the key to understanding the very origin of mass itself. We would finally see the mechanism that decided why some particles are heavy and others are light, why the universe has the substance and structure that it does. What deeper truth could we uncover by meeting the silent partners of the forces that shaped reality? The final and perhaps most profound of these hidden twins would be the gravitino. If the graviton is the hypothetical particle believed to carry the force of gravity, then the gravitino is its predicted superpartner. This is not just another entry on the list, it represents the ultimate unification. The graviton itself is a theoretical particle with a spin of 2, a unique signature for a force carrier. Its partner, the gravitino, would be a fermion with a spin of 3/2, a truly exotic value that sits between the world of matter and force. This strange spin is the mathematical key that could lock gravity into the supersymmetric framework, creating a theory of supergravity. The implications are staggering, suggesting that all forces, including gravity, are ultimately manifestations of a single, underlying supersymmetric principle. Yet detecting a gravitino would be the greatest experimental challenge of all. Its interactions with normal matter would be unbelievably weak, far beyond even the ghostly neutrino. We might only ever see its influence indirectly, written into the earliest moments of the cosmos. If gravitinos were created in the Big Bang, their sheer mass and weak interactions could have dictated the very expansion rate of the infant universe. They might have shaped the distribution of galaxies we see today. The hunt for this particle is a hunt for the final piece of the puzzle, the one that would truly weave gravity into the fabric of everything else. What secrets of cosmic creation are locked within the identity of gravity's silent twin? This elegant cancellation is the theoretical answer to a deeply unsettling question, the hierarchy problem. Why is gravity so incredibly weak compared to the other fundamental forces? A magnet can lift a paperclip, effortlessly defeating the gravitational pull of the entire Earth. This is not a small difference, it is a staggering imbalance of around 36 orders of magnitude. Our universe operates on wildly different energy scales, and the Higgs boson sits right in the middle of this puzzle. The mass of the Higgs is what sets the scale for the masses of all other particles, and it is surprisingly light. According to our best calculations in the Standard Model, this should not be the case. The Higgs field interacts with all other particles, and through quantum fluctuations, these interactions should constantly push its mass upward to the highest possible energy scale, the Planck scale where gravity becomes strong. This would make the Higgs, and by extension every atom in your body, astronomically heavier than they actually are. The universe as we know it would not exist. So why is the Higgs mass so small and stable? This is the hierarchy problem, and it points to a fine-tuning in the laws of physics so precise it seems like a miracle. Supersymmetry offers a way out of this conundrum that feels less like a miracle and more like a natural, built-in feature of reality. For every particle that interacts with the Higgs and tries to push its mass up, there is a corresponding sparticle that pushes it down with equal and opposite force. The electron tugs the Higgs mass one way, but its superpartner, the selectron, tugs back with precisely the same strength. The top quark exerts a huge upward pull, but the stop squark provides a perfect counterbalance. It is a cosmic dance of perfect cancellation happening at every moment at the most fundamental level. The universe is not finely tuned by chance. It is kept stable by a hidden symmetry, a secret partnership that maintains the delicate balance allowing our world to exist. Without these sparticles, the lightness of the Higgs is a profound mystery. With them, it becomes the most natural outcome imaginable. This perfect cancellation does more than just stabilize our universe. It points toward a far grander unity. For decades, physicists have chased a dream, the unification of all fundamental forces. We see four distinct forces in nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each operates with its own strength and rules, seemingly independent. But what if, in the extreme heat and energy of the Big Bang, they were not separate at all? What if they were once a single, primordial superforce? Our best attempts to test this idea with the Standard Model run into a frustrating problem. When we mathematically project the strengths of the electromagnetic, weak and strong forces back to those incredible energies, their paths almost meet but not quite. The lines on the graph converge, then frustratingly diverge, missing their mark. They fail to unify at a single point. This is where supersymmetry changes everything. By introducing the entire family of superpartners, we are not just adding new particles, we are adding new pathways for quantum interactions. These sparticles subtly alter the way the forces evolve as energy increases. When we recalculate with supersymmetry included, something beautiful happens. The lines representing the force strength which once diverged now bend. They sweep gracefully toward one another, intersecting in a single, precise point. This is a powerful prediction. It suggests that at an energy scale of around 10 to the 16 gigaelectronvolts, the electromagnetic force, the weak force, and the strong force lose their separate identities. They merge into one unified force governed by a single, elegant law. The universe we see, with its seemingly separate interactions, is a frozen, broken symmetry of a much more perfect and simple past. Supersymmetry provides the missing piece that makes this grand unification not just possible, but mathematically inevitable. It hints that the chaotic zoo of particles and forces we observe is merely the cooled and crystallized remnant of a far more symmetric and beautiful reality. What would it mean to finally glimpse that underlying perfection? This hidden stability of the lightest supersymmetric particle is the key to its cosmic role. Among all the sparticles, one must be the lightest, and crucially, it must be stable, unable to decay into anything else. This lightest supersymmetric particle, often the neutralino, is more than just a theoretical necessity. It is a perfect candidate for the very substance of dark matter. Its properties align precisely with what we require from this invisible cosmic architect. It is massive, providing the gravitational pull to hold galaxies together. It is electrically neutral, so it does not absorb or emit light, rendering it completely invisible to our telescopes. Most importantly, it is a WIMP, a weakly interacting massive particle. This means it feels only gravity and the weak nuclear force, the same force responsible for radioactive decay. Its interactions with normal matter are so incredibly feeble that trillions of these particles could be passing through your body every second without a single trace. This weak interaction is a double-edged sword. It explains why dark matter has remained so elusive, yet it also allows these particles to behave in exactly the right way to shape the universe. In the hot, dense early cosmos, neutralinos would have been created in abundance. As the universe expanded and cooled, their weak interactions meant they could not annihilate each other quickly enough. A vast relic population would have frozen out, left behind as a permanent, invisible component of reality. This remnant sea of neutralinos did not simply linger. It began to clump together under its own gravity, forming vast diffuse halos. Every galaxy, including our own Milky Way, is embedded within one of these enormous dark matter spheres. This is the invisible scaffolding, the cosmic framework upon which the glittering structure of stars and gas is draped. Without this dark matter halo, a galaxy's rotation would tear it apart, flinging stars into the void. The very existence of stable, long-lived galaxies is a powerful, if indirect, testament to the presence of something like the neutralino. The hunt for this particle is not merely an academic exercise. It is an attempt to complete our map of the cosmos, to finally put a name and a face to the dominant form of matter in the universe. What would it mean to finally confirm that we are living in a world built by ghosts? Hunting these theoretical phantoms requires the most ambitious scientific instruments ever built. The primary weapon in this search is the particle accelerator, a machine designed to recreate the violent conditions of the early universe. The most powerful of these is the Large Hadron Collider, a 27-kilometer ring buried deep beneath the border of France and Switzerland. Inside its circular tunnel, two beams of protons are accelerated in opposite directions to within a whisper of light speed. At 4 specific points around the ring, these beams are forced to cross, resulting in billions of proton collisions every single second. Each collision is a microscopic fireball of pure energy, a fleeting moment where the ordinary rules of matter are suspended. In this primordial chaos, energy can spontaneously coalesce into new forms, and for a fraction of a nanosecond, a sparticle like a squark or a gluino could flash into existence. The challenge is that these superpartners are incredibly unstable. They decay almost instantly into cascades of lighter, more familiar particles. Physicists are not watching for the sparticle itself, but for the debris it leaves behind. They look for specific patterns in that debris, or for the telltale sign of missing energy, a momentum imbalance that suggests something invisible and massive carried energy away from the collision point, a ghost in the machine. But accelerators are not the only way to search. A second, quieter hunt is underway in deep underground laboratories around the world. Shielded from cosmic rays by a mile of solid rock, experiments are waiting for a different kind of signal. If the lightest supersymmetric particle, the neutralino, truly is dark matter, then our entire galaxy is swimming through a vast sea of them. Billions are likely passing through right now. These experiments use ultra-pure crystals or vats of liquid xenon in the hope that, very rarely, a passing neutralino will bump into the nucleus of an atom in the detector. This would create a tiny flash of light or a minute electrical charge, a single, faint whisper from the dark universe. This global hunt, from colossal colliders to silent underground observatories, represents humanity's collective effort to answer one of the most profound questions we can ask. Are we alone in the universe, or are we merely one half of a cosmic partnership, living in constant, unseen company with our silent twins? These colossal machines are our windows into that hidden cosmic mirror. The Large Hadron Collider does not simply observe nature, it recreates its most violent primordial moments. Within its circular tunnel, protons are accelerated to within a hair's breadth of light speed, guided by immense superconducting magnets chilled to temperatures colder than outer space. When these two opposing beams are steered into a head-on collision, the result is a microscopic fireball of pure energy, a fleeting pocket of the early universe. In that chaos, energy is not destroyed but transformed. For an almost unimaginably short instant, the incredible concentration of energy can coalesce into new forms of matter, potentially giving birth to the very sparticles we have been searching for. A squark or a gluino could flicker into existence, a ghost from the symmetric past. But these superpartners are profoundly unstable. They decay almost instantly, vanishing back into the familiar particles of our world. This is why we cannot see them directly. Instead, we must become cosmic detectives, looking for the fingerprints they leave behind in the aftermath. The most telling clue is something that is not there at all, a phenomenon physicists call missing energy. Picture the aftermath of a collision. Enormous detectors like Atlas and CMS, each a cathedral of intricate electronics, map the trajectories and energies of every particle that bursts forth. We can account for the total energy before the crash and measure the energy carried away by all the particles we can see. If there is a significant amount of energy that simply vanishes, that is our signal. It suggests that an invisible, massive particle was created and then fled the scene, carrying its energy with it beyond our ability to detect. This missing energy is the scream of a sparticle, the definitive signature that we have briefly touched the hidden universe. So why, after years of searching, have we not found this clear proof? The answer may lie in the sheer mass of these superpartners. Our current collisions, while immensely powerful, might simply not be energetic enough to produce the heavier sparticles. They could be lurking just beyond the energy frontier we have so far been able to probe. Every increase in the collider's power pushes that frontier back, scanning higher masses and brighter energies for any trace of that missing energy. The search continues not as a failure but as a process of elimination, narrowing the possible hiding places for these cosmic twins and guiding us toward the energies where they must finally reveal themselves. The silence from our most powerful experiments points toward a profound truth. If supersymmetry is real, its perfect symmetry cannot be intact today. The universe we inhabit is clearly lopsided, a place where electrons are light and their superpartners are nowhere to be seen. This tells us that supersymmetry, if it exists at all, must be a broken symmetry. Think of it like a perfectly forged metal rod. In its ideal state, it is perfectly straight and symmetrical. But if you heat and bend it, that symmetry is broken. It is still the same piece of metal, but its form has been altered. In the same way, the pristine symmetry between particles and sparticles must have been broken as the universe cooled from the Big Bang. This breaking is the very reason why sparticles are so immensely heavy, placing them beyond our current reach. The elegant cancellation that stabilizes the Higgs boson still works, but now the partners doing the cancelling are not perfect mirrors. They are the bent and heavy versions of their ideal selves. This concept is known as supersymmetry breaking, and it is not a flaw in the theory. It is the essential feature that makes the idea compatible with our lopsided reality. Without this breaking mechanism, we would expect to have already found a selectron with the exact same mass as the electron, and that is clearly not the case. So how exactly does this symmetry break, and what sets the tremendous mass scale for these hidden twins? Physicists have explored several compelling mechanisms. One leading idea involves a hidden sector of particles that only interact with our own world through the feeble pull of gravity. In this secluded realm, supersymmetry could have broken spontaneously, and that breaking then leaked into our visible sector, giving all the sparticles their heavy masses. The most popular method for this transfer is called soft breaking. It is a gentle way to break the symmetry, one that preserves the beautiful cancellations that solve the hierarchy problem while still making the sparticles massive. Imagine our cosmic mirror not shattering but simply becoming fogged, distorting the reflections just enough to make them unrecognizable. Soft breaking does exactly that. It adds mass to the sparticles without introducing new mathematical inconsistencies that would ruin the theory's explanatory power. But just how heavy are these sparticles? The answer is written into the very problem supersymmetry aims to solve. To effectively stabilize the Higgs mass, the superpartners of the top quark, the stop squarks, cannot be too heavy. Their cancelling effect must be timely and precise. This suggests that at least some sparticles should be within the energy range of the Large Hadron Collider, tantalizingly close to discovery. Yet other sparticles, like the gravitino, could be vastly heavier, their masses set by entirely different scales in the cosmos. This hierarchy of sparticle masses is not arbitrary. It is a direct reflection of how the symmetry broke, a frozen record of a pivotal moment in cosmic history. The fact that we have not yet seen them does not mean they are not there. It means we are still learning to read the map, still calibrating our instruments to the specific, broken shape of a hidden universe. This search for a broken symmetry leads us to its most elegant and minimal form. The minimal supersymmetric standard model is the simplest possible universe we could build with these ideas. It takes our entire standard model with all its quarks, leptons, and force carriers and gives each one a single super partner. It then introduces just a handful of new parameters to describe how this symmetry is gently broken, giving the sparticles their heavy masses while preserving the miraculous cancellations. The MSSM is a masterpiece of theoretical economy, a framework that is both powerful and precise. It makes concrete, testable predictions. It tells us, for instance, that the Higgs boson should be relatively light, a prediction spectacularly confirmed with its discovery. It insists that the lightest supersymmetric particle is stable and neutral, a perfect dark matter candidate. The model is a complete, self-contained picture of a hidden universe, one that solves multiple cosmic puzzles with a single, elegant stroke. Yet for all its beauty, this minimal world is just the beginning. The landscape of supersymmetry is far richer and more varied. Physicists have explored countless extensions that move beyond this minimal picture. One compelling direction is the next-to-minimal supersymmetric standard model, or NMSSM. This theory introduces a new singlet field, a particle that does not feel any of the known forces. This seemingly small addition has profound effects. It can naturally explain why the Higgs mass is what it is without requiring delicate fine-tuning. It can also provide new ways for sparticles to interact and decay, opening up entirely new pathways for discovery at our colliders. The existence of these extended models shows that supersymmetry is not a single, rigid theory. It is a vast and flexible framework, a language for describing a hidden sector of reality that could be far more complex and interconnected than we ever imagined. The silence from our current experiments might not be a rejection of the idea, but a clue that the truth is more nuanced, waiting in a model just beyond the minimal. What other layers of cosmic complexity are we only beginning to map? The stability of our universe might depend on these silent partners. That delicate balance maintaining the Higgs field is not just a theoretical curiosity. It is the bedrock upon which all matter is built. If that balance were to falter, the very mass of particles could become unstable, leading to a cosmic catastrophe where atoms simply dissolve. Supersymmetry provides the hidden scaffolding that prevents this, a fail-safe mechanism woven into reality itself. This cosmic-level stability could one day become a technological principle. Imagine energy generation that does not rely on burning fuel or splitting atoms, but on tapping into the latent stability of sparticles. We already know that selectrons, the electrons' twins, could form incredibly dense and stable structures. A battery built from such a material would not just hold a charge for years, it might hold it for centuries, its energy locked in a state of perfect quantum equilibrium. Think of entire cities powered by a single, marble-sized energy core, a device that draws its longevity from the same principles that keep our universe from flying apart. Even more speculative is the role sparticles could play as catalysts. In chemical reactions, a catalyst lowers the energy required for a transformation without being consumed itself. Now picture a sparticle acting as a catalyst for energy production on a grand scale. A neutralino, interacting only through the weak force, might be used to trigger nuclear fusion at room temperature, providing a clean, limitless power source. These are not just incremental improvements, they represent a leap to a Type II civilization on the Kardashev scale, a society that harnesses the power of stars not by building Dyson spheres around them, but by mastering the fundamental symmetries that make those stars possible in the first place. The same hidden physics that gives mass to the cosmos could one day power it. The very same quantum stability that protects our universe could become the foundation for a new technological age. Computation, as we know it, is built on the restless dance of electrons, but what if we could build a computer from their silent, stable twins? The selectron, with its placid, zero-spin nature, offers a tantalizing possibility. It would not be plagued by the same quantum decoherence that makes building large-scale quantum computers so difficult. Our current qubits are delicate, easily disturbed by the slightest environmental noise. A computer built from selectron-based qubits could maintain its quantum states for vastly longer periods, perhaps indefinitely. This is not just a faster computer, it is a fundamentally different kind of processor. It could solve problems in seconds that would take classical supercomputers the age of the universe to crack, from designing complex new medicines atom by atom to modeling the entire global climate with perfect precision. And the photino, the photon's elusive matter twin, could play an equally transformative role. In a photino-based system, information might be processed not with electric currents, but through the manipulation of weak force interactions. This would create a computer virtually immune to electromagnetic interference, a machine that could operate in the most extreme environments or at the very core of a star. The revolution would not stop at raw power. These sparticle processors would operate on principles of supersymmetric logic, where every calculation is mirrored by a parallel process in the superpartner state. This intrinsic duality could allow for a form of error correction that is woven into the hardware itself, making these computers unimaginably reliable. The shift from electron to selectron would be as profound as the jump from vacuum tubes to silicon chips, unlocking a computational frontier where the very concept of a processing limit is redefined. Our entire digital world, from artificial intelligence to virtual realities, would be reborn from the bedrock of this hidden cosmic symmetry. Squarks could unlock a new periodic table of elements built not from atoms, but from stable configurations of matter we have never before handled. The strong nuclear force mediated by gluons is the most powerful binder in nature, confining quarks within protons and neutrons. Now imagine the superpartner to this force, the gluino. Its unique properties as a Majorana particle, matter and antimatter in one, could allow it to act as a perfect catalyst for nuclear fusion. A material infused with or structured by squarks might not just be stronger than diamond, it could be actively stable, its atomic bonds constantly reinforced by these hidden interactions. We could engineer substances that self-heal from radiation damage or maintain their integrity under pressures found at the heart of a neutron star. This is the promise of supersymmetric materials science, moving beyond the chemistry of our world to the physics of a hidden one. The very framework of our built environment, from the bones of skyscrapers to the hulls of spacecraft, could be reinvented with properties that seem like magic to us now. The journey between stars is a fight against distance and time, a challenge that demands a revolution in propulsion. Our current rockets are crude firecrackers compared to what might be possible if we could converse with gravity itself. The gravitino, as the superpartner to the graviton, represents the deepest point of contact between supersymmetry and the force that shapes the cosmos. While manipulating gravity directly remains a far-off dream, understanding the gravitino could reveal the quantum structure of spacetime. It might show us that gravity is not a monolithic force, but a tapestry woven from particles and their superpartners. This knowledge could lead to propulsion systems that do not push against anything, but instead gently reshape the local gravitational field. A ship could surf the fabric of space-time, contracting the vacuum in front of it and expanding it behind, effectively riding a wave through the cosmos without violating the speed of light. This is the fabled Alcubierre warp drive concept, and while it currently requires forms of matter that do not exist in our standard model, a supersymmetric universe, rich with gravitinos and other sparticles, might just contain the very ingredients needed to make it a reality. The silent twins of our known particles may hold the blueprints not just for new materials, but for the very engines that will carry us to other suns. The furnace of the Big Bang was the one era where these cosmic twins were not hidden at all. In that primordial inferno of unimaginable heat and density, energy was so concentrated that the distinction between particles and sparticles would have blurred into irrelevance. Both families existed in a state of thermal equilibrium, constantly colliding, transforming, and being created from the raw energy of the newborn cosmos. Supersymmetry was not a broken symmetry then, it was the law of the land. In this hot, dense soup, sparticles were not rare phantoms. They were as common as photons or electrons, fundamental players in the universe's first moments. Their presence would have directly shaped the nuclear chemistry of creation. As the universe expanded and cooled in those first critical minutes, the rates at which protons and neutrons fused to form the first atomic nuclei were dictated by the fundamental forces. Sparticles, interacting through these same forces, would have altered the background hum of quantum activity, subtly changing the probabilities of these primordial nuclear reactions. The final cosmic abundance of hydrogen and helium, the very fuel for the first stars, might carry the faint fingerprint of sparticles that vanished long ago. Their influence did not stop with the first elements. The gravitational pull of stable sparticles, the very same neutralinos that now form dark matter, began to work immediately. While ordinary matter was a turbulent sea of radiation and plasma, pushed and pulled by light, these weakly interacting sparticles were calm and stable. They started to clump together under gravity, forming the first gravitational seeds in the cosmos. These tiny, invisible knots of sparticle matter became the gravitational wells into which ordinary hydrogen and helium would eventually flow, serving as the hidden framework for the very first galaxies. The vast cosmic web of galaxy clusters and superclusters we map today, with its great filaments and empty voids, might trace its origin back to a microscopic pattern laid down by a sea of decaying sparticles. The structure of our modern universe, in all its glittering complexity, could be the final echo of a time when the cosmos was perfectly symmetric, a frozen relic of a partnership since lost to time. From the familiar cast of electrons and quarks to the ghostly promise of selectrons and squarks, this journey reveals a cosmos of stunning depth. We began with the particles we know, the building blocks of everything we can see and touch. Yet this visible world is just the surface. Supersymmetry invites us to peer beneath, into a hidden realm of partners for each one, a cosmic mirror reflecting a reality we are only beginning to grasp. This is far more than a theoretical exercise. It is a framework that solves the deepest puzzles of our existence. It offers the elegant cancellation that keeps the Higgs boson, and thus all mass, stable. It weaves the fundamental forces together into a single, beautiful tapestry, suggesting a unified origin in the fires of the Big Bang. And it provides a perfect, tangible candidate for the dark matter that forms the invisible skeleton of our universe, the neutralino whose silent gravity holds galaxies together. The search for these sparticles is not a niche pursuit. It is one of the most thrilling adventures in modern science, a quest to validate a symmetry that could be the master key to physics. Unlocking this next chapter would not only explain the cosmos as it is, but could launch technologies we currently relegate to science fiction, from perfect quantum computers to engines that bend space itself. This search continues in colossal colliders and silent underground labs, a global effort to answer a fundamental question. Are we alone in the universe, or are we living in constant, unseen partnership with our cosmic twins? I would love to hear which of these hidden particles captures your imagination the most. Is it the stable selectron, the cosmic architect neutralino, or the gravity-weaving gravitino? Let me know your thoughts in the comments below.